Hey everybody, what's going on? So today we're going to be talking about periods on a periodic table and what they represent, as well as groups slash families, and what they represent on a periodic table. But before we get started on anything, remember that the atomic number is always going to be equal to the number of protons and the number of electrons. And if you subtract your atomic number from the atomic mass, that'll give you the number of neutrons. So that right there gives you your protons, your electrons, and your neutrons, and you're on your way to drawing your Bohr model, hopefully soon. If you ever need to identify what atom you're looking at, what element that atom represents, you got to do one thing, and that is look at the protons and count the number of protons. You can always identify any atom by counting the number of protons. Now, as far as you know, again, the number of protons and the number of electrons is always equal. So if you can't count the protons, you're more than welcome to count the electrons, and that'll tell you what element that is as well. Now, if we look on our left-hand side, right over there, we have a bunch of numbers going from 1 to 7. Those have a very important significance. This periodic table wasn't just thrown together just in any way. It's put together in very specific ways that we'll talk about throughout the year. So on the left hand side we have 1 through 7, and those are called periods. And what those specify are the number of energy levels, shells, or orbitals that an element has whenever you're drawing its atomic model, or its Bohr model. Now, you see that it's ranging from 1 to 7. That just tells you the number of shells that element has. So 1 is going to have 1 shell around it. 2 is going to have 2 shells around it. 3 is going to have 3 shells around it. 4 is going to have 4. 5 is going to have 5. 6 has 6. And then 7 has 7. And these are categorized in rows, which means that every single one in that row is going to have the same number of shells. So hydrogen and helium are going to have 1. Lithium, beryllium, boron, carbon, nitrogen, all are on row 2 or period 2. They're all going to have 2 shells. Period 3, all of that row is going to have 3. 4 is going to have 4. That entire row, so on and so forth. Now, if we look at the very top, we have something else called groups or families. They go by either name. And there's a reason why they go by groups or families, and that's because they have similar characteristics based on the groups or families that they're in. So if you look at the very top, they are numbered from 1 to 18, and what these give you is the number of valence electrons. So a valence electron, which we tend to abbreviate with a V and an E, it's the number or the amount of electrons that you find in the outermost shell. And what that means is that it's just the amount of electrons that are in the last shell of that atomic model. So if you have 1 shell, the electrons in that shell are your valence electrons. If you have 2 shells, the first shell is not your valence electrons. Your second shell is going to have the valence electrons. If you have 3 shells, the third shell is going to be where your valence electrons are. If you have 4 shells, the fourth shell. So, you can tell how many valence electrons each one has by looking at the number on top. So if we look at the first column, which is what goes up and down, it's vertical. Column 1, you see a 1 at the very top. So that tells me that whole column, hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium, all have 1 valence electron in their last shell, in their last circle. With these, it's a little different. We don't talk about the middle ones going from 3 all the way to 12. They have different properties, so we skip over to number 13. So ignore the ones in the middle. They have different properties. We skip over to 13. So for 13, we circle the 3. For 14, we circle the 4. For 15, we circle the 5. 16, 6. 17, 7. And for 18, 8. And these tell you the number of valence electrons. So the first group is going to have 1. The second group's 2. 13th group has 3, the 14th group has 4, the 15th group has 5, the 16th group has 6, the 17th group has 7, and then the 18th group has 8. With that being said, the 18th group, which has 8 valence electrons, there is one exception, and that is going to be hydrogen. Because if you remember how many electrons hydrogen has, hydrogen only has 2 electrons. So there's no way that it can have 8 valence electrons on its outermost shell because it has only a maximum of 2. So it's the only exception. The rest of them are going to have 8, except for hydrogen or helium. Sorry, helium only has 2 valence electrons. Everyone else in group 18 has 8 valence electrons. So valence electrons are read in columns, which go, again, up and down. So this is a column. It is vertical. So they're read in columns. So again, everything in that column is going to have the same number of valence electrons. So again, up and down. It's vertical. Periods are read horizontally, that entire row. For valence electrons, that entire column going up and down. So all elements in that same column have the same number of valence electrons. And again, that's pretty simple to memorize. So again, group 1, which is the one where you have hydrogen, helium, or hydrogen, lithium, sodium, those again all have 1 valence electron. So again, that entire column is going to have 1 valence electron. That means that in its last shell, it's going to have only 1 electron. So for francium, francium being the last one on there, francium has 7 total shells. That means that it's on its 7th shell, there's only 1 electron on there. We move on to group 2, beryllium, magnesium, calcium. All that column has 2 valence electrons. So that means on its last shell, you're going to find 2 electrons. So again, if we talk about beryllium, beryllium has 2 shells. On its 2nd shell, you're only going to find 2 electrons. And it just gets more, not that it gets difficult, but as you get more shells, obviously it gets a little bit more complicated. We won't get anywhere near the 7th shell. It would just take way too long to get there, or to do one of those Bohr models. But you'll see the process as we go when we build Bohr models. So again, everything in that in that column, going up and down, is going to be the same number of valence electrons. Now, again, we don't really talk about the ones in the middle. They have different properties that we just do not discuss. They're called transitional metals, and it doesn't really work for those. The amount of valence electrons differs, so we don't talk about those. And also the lanthanides and actinides, different properties. We don't talk about those, so we just kind of skip those. Again, we go from group 1 to group 2, then we skip over to group 13, 14, 15, 16, 17, and 18. And then for 13 through 18, we use the last number. Again, 13, 3, 14, 4, 15, 5, 16, 6, 17, 7, and 18, 8 to figure out the number of valence electrons. Again, there is that one exception on group 18, and that's going to be helium. Again, helium only has 2 electrons, and you can figure that out by looking at the atomic number being 2. So valence electrons don't only tell you the number, or a group doesn't only tell you the number of valence electrons, it also tells you what kind of reactivity that element's going to have. So is it super explosive? Is it not explosive? If you're in the same column, you're going to have very similar characteristics. The number of valence electrons does dictate how reactive you are. So valence electrons tell you how reactive or non-reactive an element is. If the element's in the same group, they'll have similar properties and characteristics.